Thank you, Annika. Well, this presentation is telling about radionuclide analysis and the detections what we had during this period of accident, and also about how we prepared for it. To start up with, even when the accident in Fukushima was not going on, we started the preparation because we knew that something may happen. So we stopped things that were not necessary, for example, scheduled maintenance and calibration and spiking experiments to make sure that we have the highest possible level of the data availability in the system. In addition to that, we started to model by atmospheric transport modeling forward to see where the radionuclides possibly originating from the Fukushima would be seen in the first place. So because the transport takes a couple of days from source to the station, we had actually about 2 days time to prepare all of this. Then situation started to develop, and we started to have the detections in the radionuclide system. First, I'm going to show you an animation which shows how our international monitoring system was detecting the Fukushima release. First, have a look on the red dots. They mean that this location has detected at least 2 or more fission products originating from the Fukushima. It took less than 1 week until the release was reaching the western coast of America. After that, Eurasia, and within 3 weeks, all the stations are shown here in this map, including the 2 ones in the southern hemisphere, detected the plume. Then the dots will turn in the green, and this is actually part of our verification job. This means that we still see those radionuclides, but they are typical for the station, so they are not causing us, from CTBT verification point of view, any alarm. When the time goes by, these stations are turning in the blue. This means that the station is back to the normal background radiation, so we don't see any more fission or activation products in those stations. In total, this whole period of hot season took about 2.5 months, during which about 1,600, 1,700 samples of particulate were affected, at least with iodine, and about 400 of those were of the highest level, level 5. You see here the profile of these detections as we have seen in the system. Talking about the levels of the radioactivity, what we saw. First of all, this is a station JPV-38, Takasaki, Japan. It is about 200 kilometers southwest from Fukushima, so this is the closest station what we have in the system. First, we have a couple of isotope profiles here as presented as a time. The highest most is xenon-133. Because xenon is a gas, it really escapes easily in this kind of situations, and concentrations went pretty much higher than the particulate ones. Here we will see that highest value what we measured was in the range of kilobecquerel per cubic meter. But like Emmy was pointing out, we were actually pretty close to the dynamic range of the measurement system. So the actual concentration may be in the range of up to a few tens of kilobecquerels. Xenon is in a way easy isotope because it is not posing so big danger for human beings as it is inert noble gas. What is more important from the health point of view are the particulate and the solid ones, and especially the iodine, which is posing the biggest risk for the human health. In this graph, you will see a couple of other isotopes presented. First, the green one is cesium-137. That's a long-lived radionuclide which also escape in this kind of situation relatively easily. Blue line here, light blue line here is iodine-133, and you will see that by the time goes by, the iodine level goes down, as it has an 8 days half-life. Then we have a couple of other isotopes. The red one is niobium-95, and the remaining one is lanthanum-140. What we see immediately from this picture is that what we talk here about is the gaseous release. So xenon is a gas, iodine is mostly a gas, cesium is gas if the temperature is over 700 degrees, And one more isotope, tellurium, is a gas which is, if the temperature is above 1000 degrees. So this is providing us already a thermometer on what is the temperature in the reactor. Another good information here is that we don't see too much solid components in these samples. And if we, for example, compare this to Chernobyl, in Chernobyl the reactor was burning and big part of the solid material were actually escaping from this reactor. This was not the case in Fukushima, and from health point of view this was really good news for experts who were analyzing this one. Another way of looking at the detections is to see the isotopic ratios. Here I have plotted the isotopic ratio from different isotopes versus cesium-137. It's typical that you will see this kind of oscillation. For example, iodine to cesium ratio is not a straight line. This is because in the atmosphere these two substances are traveling different way. One is solid particle and the other one is mostly gas. So this is so-called fractionation, which we will see typically in this that kind of system. And then what we see here also is that there are two isotope ratios which are very static. One of them is cesium-137 ratio. Throughout the whole period of time to the end of April, the ratios remain the same. So it is a good indication that we are talking about the same release. However, here we will see cesium-136 to 137 ratio. It is also supposed to be on this straight line because it's the same element, so it is supposed to travel the same way. However, around the 1st of April, there was a dip down of this ratio. And in the same time, actually, the concentration went up. This is actually an indication that maybe we have here a mixture of the different material of different cooling time together. And this is very well in line with the information that some of the reactor storage bonds may have also dried out. Thank you.
Thank you very much, Mika. We take a quick break because I understand that we have our colleagues from UNESCO with us again. I apologize very much for the broken video link in the earlier session, and I also know that you will be with us until 1 o'clock, and I very much would like to give you the opportunity to comment on the make the comment from the earlier session if you care to do so. Please, you have the floor.
Well, thank you very much. It's not that we have any substantial comments from here. We thank you very much for the invitation, and we have enjoyed the presentations, and it underlines the fruitful collaboration that the executive secretary also that we have with CTBTO. So I think I just want to say thank you very much to the presenters and look forward to hearing to the questions and answers.
Thank you very much. We appreciate very much your participation. We will go back to the presentation by Mika, please.
Yes, thank you. Considering the levels of the radionuclide detected, first of all, in Japan, as you saw in the graph previously, we were in the level of few tens of becquerels per cubic meter of radioactive iodine. Iodine collection efficiency has a little bit of peculiarity, so we can anyway say that we are in the level of tens rather than hundreds of becquerels. Considering the other monitoring stations, we were typically in the level of up to few tens of millibecquerels. So outside of Japan, all the stations were showing us 1,000 times lower concentration. This was, of course, very good news from the health point of view. In the radiation protection point of view, these levels of the radiation are still not considered harmful for human beings. For example, if you compare the dose what you receive during the typical transatlantic flight, the level is much higher compared to what you have seen in this. What is the dose rate related to the Fukushima release even in the highest station. Second thing is that we of course provided this accurate information about the concentrations for stage parties, and each of the stage party will have to have the Radiation Protection Authority, the competent authority who is providing the information for the stage parties themselves, how to react on this kind of situation. And they are the authority who will explain the risks. There are also international organizations treating the radiation protection issues and the impact of the radiation for the health, and especially this is IEA and WHO, and they may also provide guidance and recommendations within their own level. Then we had, after this Fukushima accident, of course it was a big test for our system, so we learned a lot about the details. There were quite a lot of spin-offs technically and practically what we have seen in this system. Emmy already informed us about this use of the lanthanum bromide detector based on the real-time monitoring to enable us to enhance the dynamic range of the measurement, to have the quicker response, and also to provide information for the health and safety point of view. It's not only the equipment, we also have to be able to analyze the data and understand how to do it automatically and how to warn the station operator quickly in case of this is happening. With this one, depending on the level of the radioactivity, we can respond back in minutes in case something is seen at the station. Then the International Data Center was studying alarm system, which is then providing accurate and timely alarm whenever abnormal radiation is seen in the station. This system is providing email messages for the users to wake them up in the middle of the night if necessary to respond to the situation. This system was actually set up during this accident, and it was providing us very good warning system when the radiation level was monitored. Then we provided a new tool for the state parties. It is part of our website, tool called CR Tool. This is a graphical tool which provides you the graphs on the development of the radiation as seen in the IMS network. The pictures that I showed you previously were actually coming from this tool. Then this whole dataset, this 1,600 samples, provided us very good dataset also to improve our capabilities in the IDC software. We actually rolled in a new version of the software last year in June, and we were really using the Fukushima test set as a baseline for the acceptance of this software. Then it also started up the procedural consideration, so how are we really treating the hot samples at the station, and are there radiation protection issues related? This is an issue because even if the level of the radiation in the air is not dangerous, our system is actually condensating the dust in the filter, which may then have 20,000 times higher concentration in the filter than in the cubic meter of air. This is to be considered. Then we were also considering the improvement of the atmospheric transport modeling, and how do we do automatic things, and how we quickly provide the presentation and the risk pictures. Monika is going to provide more information about the atmospheric transport modeling, but this is one issue which is also under development with us. Concerning the source term, it was also mentioned during the first part of this presentation. We started with initial value, and after the cooperation with IEA, we started to refine it. So in the end, in a couple of weeks, we had a good estimate which was adequate to assess the situation in the global range. This data was further elaborated by WMO, and the study is still going on. And as Professor Weiss was also mentioning, Ansgar is doing really detailed analysis of this data. It is very important to reiterate this national contribution of Japan to improve the atmospheric transport modeling infrastructure within the PTS. And to remind you that Japan has also called other state parties to contribute as well, because it has proven to be a very important part of the system. I show you very briefly about the reports what we are typically presenting in this kind of situation. The report is called RRR, and it's called Reviewed Radionuclide Report. This is produced for each sample, and to have the quick view on it, I have highlighted a couple of issues which are important in this one. First of all, in the first sample information, we have the station coordinate, the location of the station, the volume of the air sampled, and the time when the collection and the acquisition was done. If you look down here in the bottom line, there is one comment which is very important. It says that this is confirmed as level 5 due to the presence of the activation and fission products. This means that we have categorized this sample as level 5. This is actually pretty important from the quality point of view, because this ensures that we trust the sample concentrations. Categorization is based on each individual isotopes, and we provide also information on isotope-wise why this is now level 4 or level 5, for example, in this case. On one big part of the report is also the activity summary. So here we provide the information on the radionuclides detected and their concentration, which is very important for the people who are assessing the radiation risks, for example, in addition to the 3D monitoring. Now I turn to Monika, who will continue on atmospheric transport modeling.
So indeed, I'll give more details about atmospheric transport modeling in this How do I move? Okay. So I'll give more details about an atmospheric transport model that we run at PTS. An atmospheric transport model is a numerical model which simulates the phenomena of advection and diffusion of trace gases throughout the atmosphere. The trace gases in question for the CTBTO mission are radionuclides. And in order to produce an output, an atmospheric transport model requires an input. The most important input information is provided by the meteorological fields. The more detailed input information depends on whether we run an atmospheric transport model forward or backwards in time. In the forward mode, which is used to assess the field of activity concentrations coming from a known source, it is important to provide the model with the location of the source and the temporal profile of the emission. For a backward mode, when we look for a field of sensitivity of a given measurement to the location of the source term, we need to provide the atmospheric transport model with the information on when the measurement is taken and what's the duration of a measurement interval. This is this backward mode that we normally use to support the CTBTO mission. However, during the Fukushima event, we run an atmospheric transport model in a forward mode in order to assess the propagation of a plume of radionuclides. The model that we run at CTBTO is FlexPert, and we produced the FlexPert outputs and we posted them on the IDC Secure website during the period between the 15th of March and the 3rd of May 2011. We provided our authorized users with the snapshots of the simulations, the animations in a GIF format, and then animations in a KML format, which can be visualized using Google Earth. We use, as for the standard atmospheric transport modeling computations, two providers of the meteorological fields. One is the European Centre for Medium-Range Weather Forecasts, which makes available for us the meteorological fields enabling assessment of the past situation. And then the second provider of the meteorological fields is the US National Centers for Environmental Prediction, which makes available the meteorological fields valid for both past and future meteorological phenomena. The source term that we used in those runs, that we knew the location of the source because that was the Fukushima nuclear power plant. And since we had no more detailed information, we run our simulations using the most conservative assumption. And we took a source term which starts at the moment that tsunami occurred and which lasts until the end of each simulation. The quantity had nothing to do with the nuclear accident that was configured for the CTBTO mission. And this system will be enhanced in the future thanks to the Japanese contribution in terms of money to purchase computers in terms of human expertise, and that will result in CTBTO using high-resolution meteorological fields, high resolution referring to both spatial and temporal resolution, which should enhance the quality of the outputs of an atmospheric transport model. So this is what we've done during Fukushima, but normally we run an atmospheric transport model backwards in time. We run it for each radionuclide station of the IMS network and for each sample which was taken at this network. And we run it backwards in time in order to assess those regions where a source of radionuclides detected at the IMS network might have been located in the past. We refer to the outputs of this model as source receptor sensitivity fields, and a concept how we actually produce them is presented in this slide. So we have the time axis. The time points T start and T stop indicate the duration of a sampling period. The backward simulation of an atmospheric transport model starts with T stop with an adjoint release through the duration of the sampling period until T start, and then we carry on 14 days backwards in time. It is important to realize that, like for the forward simulation, the further forward in time we move, we have a more diluted plume, which affects larger geographical regions. For the backward run, the further backwards in time we move, we have the geographical region of the non-null sensitivities, which also grows in space and time. On the basis of the source receptor sensitivity fields, which are basic atmospheric transport modeling product, we construct two additional more advanced products. We refer to them as fields of regard, and we have differential and integral fields of regard. An integral field of regard, the concept behind an integral field of regard is presented in this slide. So we need two pieces of information. One is a scientific knowledge on the strength and nuclear yield of an explosion, which defines a cutoff value of sensitivity, which then defines whether an area of the surface of the Earth is within or out of an integral field of regard. And then we need also the geographical knowledge stemming from the source receptor sensitivity fields, which we merge into the geographical regions which were affected by a source receptor sensitivity field, so which were affected by the sensitivity values above a certain threshold in a period of 24, 48, 72, up to 144 hours preceding the end of the collection time. We produce those integral fields of regards on a daily basis for each station and each sample taken at the IMS radionuclide network. We append those images to reviewed radionuclide reports, and those are valid for 6 days preceding a detection. If we now have a closer look at one of those integral fields of regards, we notice that this is produced for the station RUP-60, the station located in Kamchatka in the Russian Federation. The measurement time period ended on the 18th of March 2011, and that corresponds to a detection which originates from the Fukushima nuclear power plant. So if you have a look now at this integral field of regard, you see all those areas which, according to the hypothesis, the underlying hypothesis on the source term, and according to the atmospheric transport modeling calculations, could have contained a source of radionuclides detected at the RUP-60, and you see that the location of the Fukushima falls within this integral field of regard. And now I have two more slides that refers to a different concept. This is a concept of differential field of regard, which also stems from a source receptor sensitivity. Those are also appended to our reviewed radionuclide reports. And if we now have a close look at an example of such a differential field of regard, we see that this is a snapshot of a source receptor sensitivity field, valid for a given day, a given 3-hourly time interval. What is important here that we preserve the value of the sensitivities, And this allows us to infer twofold information. On one hand, the higher the value of the sensitivity in the geographical region, the lower needs to be a release of radionuclide in order to be picked up by our station. And on the other hand, once we have the value of the measurement at the station, and we look at a particular region on the surface of the Earth, we take the sensitivity from that region and we divide the measurement by the sensitivity, we can get an assessment of a release at that particular place. So I'll stop here with the details on atmospheric transport modeling, and now it's back to Mika about CTBTO data and products.
Yes, thank you, Monika. Now that we have shown you all of this exotic and interesting data, the question, of course, is how to access it. As we remember, Executive Secretary was recalling us to have at least 5,000 users, if possible, to access the data. There's a formal procedure if you would like to have the full access to the data. First of all, there has to be a registration form submitted through the official channel. This typically means through the permanent mission of the state party to the PTS. After that, when the application has been handled, we are providing account and the password, and which can be tested, and after that, the users can access directly into our data through the subscriptions or through the website, over the internet, over the VPN, or over the satellite connections that we provide. There is an alternative, and this is for research purposes. We have set up a system which is called Virtual Data Exploitation Center, or VDEC. This system contains archived data of interesting events, which can be used for the scientific purposes, for studies and for the research, to improve further the understanding of the Earth and understanding of the treating verification. And this also can be accessed by sending an application to the IDC that you would like to have access to VDEC. How to access the data in practice then? First of all, it's possible to access through the data request manager. This means that you can send request by email, which is automatically processed by the system, and then it sends back the data what you requested. Then you could have a subscription, so you can have access to the data by setting up the system, which is then sending the data of your interest back to you. This is especially a big issue for the raw data transmission, if you would like to have access to that one. Then we are running external database service outside of the operational one. That is mirrored close to the real time with the IDC operational databases, and there the users can run their own SQL scripts and own software to test the methods. The easiest way, however, is to access through the IDC secure website. We have graphical interface to show most of the detections and most of the data, and we provide information to how to browse the data through this huge database. Lastly, on VDEC, this Virtual Data Exploitation Center, this is actually the same kind of issue like external database. So we have huge collection of the data in that one, ready for the research topics. So how does it look like in the real world? So first here in the left side, this is the front page of our secure website. This is a kind of hub where we can start to access different kind of data. For example, I was referring to CR tool, a new tool to show the trends in the radionuclide detections. It can be started directly from the front page here. Then in this lower right corner, we have a typical view on the daily radionuclide detections. It can be accessed here also through the products or through the site index of the web page. This web infrastructure is now ready and has been used for 10 years, but we have lots of ideas how to improve this further. CR tool is one starting point. We are improving the CR tool, and we are going to set up the completely new setup of the system in the coming years to make sure that the data and the products can be accessed effectively. Thank you.
Thank you very much, Monika and Mika.